Today we're taking a look at the last section in chapter 13, which is called Tessellations of the plane. Now, the pattern blocks that you guys used up here at the front, you didn't completely tessellate with them, but you guys all did some portion of what you did with tessellating ideas. So let's first talk about what is a tessellation. A tessellation of a plane is a way to fill the plane with copies of congruent figures so that there are no overlaps and no gaps. The first two pictures are like the most basic, boring tessellations you could possibly imagine, right? They look like tiling on the bathroom floor or the bathroom wall. A regular tessellation is a tessellation done with regular polygons. So let's ask ourselves if we remember, what does it mean for a polygon to be regular? Oh, you guys made me so proud. You remembered something from, really, that's quite a ways back. We talked about that. Yes, it needs to be equiangular and equilateral. Sorry, somehow I missed it. So regular tessellations are kind of cool. They make things really easy. Most of the tiles that you guys were working with here, not all of them, but most of them were regular tessellating tiles. So one of them that you had that was regular was your square, right? Equiangular, equilateral. You had an equilateral triangle that you were working with, and you had a hexagon. These were the equiangular, equilateral figures you had up here. You had some others as well, and it doesn't mean that you can't use other shapes to tessellate. They just work a little bit differently. So the first ones we're going to talk about are regular polygons. So regular tessellations, unfortunately not all regular polygons tessellate. In fact, these three are very special, okay? So the way that we decide if a polygon will tessellate is that you have to notice that at the center of every time that you have the vertices adjoining, it's 360 degrees, right? So the sum of all the angles around there have to add up to 360 degrees. So since the sum of the angles at each vertex must be 360, the number of angles at each vertex must be 360 divided by an angle measure. So what is the largest degree angle measure that I could divide 360 by and get a whole number? 360, but then I'd have a circle and I'm looking for polygons, so think a little bit smaller. 180, right? All right, so I could divide by 180, that'd be okay, but that's just side of a polygon, right? That's not actually going to create an angle that's less than 180, right? So 90. Anything else you can think of that would work? 60 would work. 45 would work. 30 would work. 15. Okay, so we're coming up with lots of different objects that would divide 360. Unfortunately, not all of them are inside regular polygons, right? Now, some of them are. Somebody mentioned 90. 90 degrees, that's going to be inside of a regular polygon known as a square. Somebody mentioned 60. It's a regular polygon known as a triangle. Nobody mentioned this guy. Do you remember what his angle measures are for the hexagon? What is it? It is. It's 120. Good job. It's 120. Do you guys remember how you figured that out if you didn't just remember that it was 120? How to do with the number of sides?
Sides minus 2.
Minus 2. So how many sides are there?
6.
6. Minus 2 would be 4. 4 times 180 gives me what? 720. But 720 is not exactly what I'm looking for. What else do I need to do now? Divide it by 6. And if I take 720 divided by 6, I'll get the interior angle of each of these angles of this polygon. Okay, so thus the angle measure for these polygons themselves must evenly divide 360. All right, so take your best guess here. Which regular polygons do you believe will tessellate a plane? Based on this discussion we're having about degree measures and so forth, which regular polygons do you believe will tessellate a plane?
Like if you put them together?
Yes, if you join them like you did with your pattern blocks, which of them will actually fill in that 360 at the corner?
Well, doesn't it, like, it's just like, you can just put all the same ones together.
Okay, But what regular polygons do you know? Give me an example of one, Madison, and we'll talk through that one. Which one?
Wouldn't a kite be regular? Or
Is a
the-
kite a regular polygon?
Oh, I'm sorry. Wait,
Not generally
what's the
speaking.
dot? I'm thinking like a diamond shape.
A rhombus?
Yeah, that's
A
what I
rhombus
was
is not
thinking.
regular. We have it up here that we use for pattern blocks, but it's not regular. Why is it not regular? Not equiangular.
A square.
Yeah. Okay, let's talk about a square. If I take a square and I put 4 squares together at this corner, whichever corner, I don't care, they'll all add up to 360, right? Right? So a square will tessellate the plane. A square works. So that's one of the ones you should write down here is square.
Your PowerPoint slide represents that too.
Yes, it does. Such nice noticing of that, Lauren. Thank you. Yeah, here's my 4. There you go. Drawn sloppy, but that's okay. Okay, so take a look then. What about this one? Triangle. A specific kind though, right? An equilateral triangle. If I took 3 equilateral triangles, what would happen if I put them all together?
It would be 180.
It would make a 180. So how many triangles would I actually need?
6.
I'd need 6. I would need 6 of these little green triangles put all together to actually make a 360 degree. And in fact, if you take a look, do you see it? That's exactly what the yellow shape is. It's 6 of the regular triangles, right? Equilateral triangles put together. So an equilateral triangle will work.
So that means a hexagon, right?
They make a hexagon. A hexagon actually works as well, and it works because we already talked about the angle measure. What was the angle measure? 120 on each of the interior angles here. 120. So how many hexagons would I have to put together to actually tessellate? I need 3. 3 times 120 is the 360, correct? But I can't have anything bigger than 120. Why not? Because it won't divide the 360 evenly. So there is no polygon bigger than a hexagon that will tessellate a plane. This is it. There are only 3. 3 polygons that will tessellate a plane. Regular polygons that will tessellate a plane. However, we can tessellate with other shapes. Okay? So non-regular polygons can be used in tessellation as well. If you take any, this is kind of a cool fact, right? Any convex quadrilateral, and you do half turns around the midpoint of the side. So let me draw that into the picture. So we'll take the black shape at the top, and if I take this side with this point right here, S, and I do a half turn, it will rotate it around like this and form this picture down here, right? I can do the same thing around the point P over here. I can take a half turn and rotate it around here. And then I can use, it doesn't matter which side I use, either of these sides, and do the same thing one more time, and I'll get this bottom shape down here. And it will tessellate a plane. Why did that work?
It's all the same shape, it's a quadrilateral, so all the angle measures.
Are they in the
add up
same-
to 360.
All the angle measures add up to 360 in a quadrilateral. So when I do all these rotating shapes, these half turns, I end up getting the 4 angles in the center that were the original 4 angles of my quadrilateral. So they add up to the 360 that I was needing. I'm
So
sorry.
so basically, if they're the same, like in the same position as the ones that are like kind of like how it's like catty corner kind of thing.
Mm-hmm.
So if they're in the same position,
Well, I don't think any of these are in the same position because we've done rotations instead.
well, okay, I guess I don't know. She's heard about corresponding. Yeah.
Oh.
Something I don't know. I just kind of see them as being the same. Like obviously this one's not on the bottom, but like I don't know.
One thing you can recognize on this though too is that this piece and this piece
That's what I was.
are mirror images. Is that what you're looking at?
Yeah.
And this one and this one?
Yeah.
That's true.
Okay.
Yeah, it doesn't work for all 4 of them, but you can take them in pairs and do that and think
Okay,
of it
that's
that way.
what I was
Yeah, and you do get all the same angles, right? So this one's angle C, And here's the angle C right there.
Yeah.
And then this one's angle D. And here's angle D rotated right here. And then here's angle B and angle B. And then I've got the last one, angle A. The angle A doesn't change. It's the same angle like from before. It's okay. All right, so, and it's all around this, they fit together at this common vertex in the center. So tessellations can be done with any shape. There's nothing really special about regular shapes. We see them done a lot of times with regular polygons, but they don't have to be done with regular polygons. Now, if we do want to use regular polygons, we can start with a shape that automatically tessellates, like a square. That's this picture you're seeing right here. And we can make some alterations with the square to make it more interesting. So another way to tessellate the plane with a non-regular shape is to take a polygon that tessellates like square and cut out a design on one side. So you can see this on the side, this sort of reddish coloring up here is a cut out shape alongside. And literally took a pair of scissors and cut the thing apart, okay? And then you have to slide that cut down to the other side so that it's a mirror image. So these look sort of parallel. You know, the cuts are identical on the top and the bottom. And it doesn't just have to be the top and the bottom. If you do the top and the bottom, you could also do the left and the right. And you could do both, right? The left and the right and the top and the bottom for a more interesting shape. Okay? Once you do that sliding, it actually fits together the same way because these are parallel, right? And you have the same image repeated over and over again. So this object is not even a polygon anymore, right? It's not just a non-regular polygon. It's not even a polygon. And it's tessellating. It's kind of cool. There's one other way that you can do this that we're going to talk about. You can start with a triangle, okay? So if you started with a triangle, you could do a hexagon with this as well. I had somebody do that one time. You can start with a triangle, and you take half of the length of the equilateral triangle, and you do an interesting shape. This one's cut out. And then you do a half turn, so you rotate that shape around down here. So see how this is cut out into it, and this is the cut out on the outside. Okay? This is what's going to allow it to fit together. So this image will fit with the image from the same image drawn the other direction now, to go backwards. Now, the goal as we're doing tessellations is going to be to look at this object and say, oh, now I see it, and it looks like something else. So when you look at this object, what does it look like to you? A what? A rock? Okay. Mountains? Bottom of what? Bottom of America. The edge, like of the coastline. Okay. Okay, so this is what you're going to be doing as you're looking at your shapes. We're about to talk about something fun here in just a second. One more piece to talk about. Your book actually talks about some other ways to make more intricate tessellations. So if you are artistic in nature and you would like to see some further information, check out pages 801 and 801 to 803. They show you how to use rectangular squares and being able to tessellate with some more interesting shapes. Think mathematical classroom art, stuff you could put on your wall. This particular artwork is done by a gentleman named M.C. Escher. He's got some cool stuff, okay? Be aware, this is your disclaimer, some of his artwork is kind of dark. Like it's kind of a little bit on the scary side. So it may not be appropriate for your classroom, all of it. I chose one that's not dark. It's not inappropriate for a classroom. And so what this is a repeating shape. Can you see it? And it looks like what? Fish. It looks like fish to me. And they've got the same shape in two different colors, oscillating back around. Actually, it's rotating. So this piece is rotating, right? And the tail piece rotates. You've got all four between into the middle. Okay? So we need to talk about what you guys are going to do related to this next.